So let's see how quadratics are used in practice. You see them used all the time in physics and engineering. The trajectory of a ball, a missile, or a rocket is actually a parabola, and it's described by a quadratic equation. Also, curves in the road are all based on quadratic equations for all you civil engineers out there. But let me give you an example in manufacturing, because you'll see this very often in manufacturing, operations, and in supply chain management. So suppose I'm manufacturing some product, let's call them iWidgets, and I want to know what price to set. Now typically, you'll know your cost function. What does it cost for me to produce these widgets? And in this case, I have a very simple linear cost function, where I say that the cost is a function of the number that are made, X. And so that will be equal to, in this case, I'm saying it's $500,000 plus $75 per each unit I produce. And that produces this linear function that's drawn here on the chart, and it's an increasing function where the slope is 75 and the y-intercept, or the constant, is 500,000. Now I'll also need a corresponding demand function. And so let's say it's a linear function based on the price P. So unit sales is a function of price, and it's going to be equal to 20,000 minus 80 times P, where this value, this should actually be a P. As the price increases, I expect to sell less. This makes sense, right? So let's look at this for a second, because this is a common demand function, as it's called. If my price is 0, if I'm giving it away for free, this function is saying that I will be able to give away 20,000. That's my market size. It's also letting us know, okay, how many or what does my price need to be to sell 0? How expensive should I make it to make sure that no one wants to buy it? And for that, you would just set that equal to 0. 20,000 divided by 80 gives you 250. So I know if I price it at $250 per iWidget, this demand function is saying I won't sell any. But it's a linear function between that. So I've got a linear function for the cost of producing them as a function of X, the number I make, and I've got a function for the demand, which is a function of the price. I want to find the profitability then. So I need to find the revenue and the cost and then subtract them. So what is the revenue? Well, that's simply going to be the number that I sell, which we just figured out from the demand function, 20,000 minus 80 times P, the price. And how much will I make? Well, I multiply that by P, right? That's what I'm charging for each one. So that turns out to be 20,000 P minus 80 times P squared. Now the costs here are simply going to be this cost function, but instead of X, how many will I make? Well, I'll make the amount that I expect to sell. So I'm just plugging that in for X. So it's 500,000 plus 75 times 20,000 minus 80P. That equals, if you carry it out, 2 million minus 6,000 P. I want to find the profitability though. So I'm just going to subtract revenue minus the costs. And if I plug this out, I end up with this equation of minus 80 times P squared plus 26,000 times P minus 2 million. Looks like a quadratic. And this is what's describing the profit function as a function of the P, the price. So this is a quadratic, so we can find the roots. If I want to find the roots of this, I'm just going to use my quadratic equation, which we all know and love, where my A value is minus 80, my B value is 26,000, and my C value is minus 2 million. And if I plug those in, I'll be able to find the roots. So I'll wait for a second while you do this. I'll wait for you. Go ahead and give it a shot. Turn the video off. Okay, hopefully you checked it out. And here's what I got. R1 equals 125 and R2 equals 200. Now if you had R1 equals 200 and R2 equals 125, it doesn't matter. You just chose to subtract or add in a different order. But end of the day, what we've done is we've described this profit function. And it's a function of P, the price. So this chart is showing on the horizontal axis the price that I'm charging per widget, and on the vertical axis the total profit. And we found these two roots. Now what we want to find really is not the roots necessarily, those are important, but I really want to find this point. Where do I maximize my profit? And I want to know what price should I set to maximize my profit. That's what we're going to learn in the next lesson. However, I want you to see that we've characterized the profit as this quadratic equation. So it's very powerful stuff, the quadratic. Let me show you one other example that I use. And this is an example of pricing in parcel truck. And so in parcel trucking, carriers will combine many different orders into a single shipment. So the cost of an individual order is typically a function of many things, but in this case, we're going to say it's a function of its weight. However, it's not necessarily linear. It actually tapers. And so let me give you an example here. So in this chart, the horizontal axis is the weight of the order in kilograms. The vertical is the cost per order in euros. So this is what the function is that I mapped up here, where cost is a function of weight is equal to 33 plus 0.067 times W, the weight, minus 0.00005 times the weight squared. And so what happens as the weight gets bigger, it suddenly tapers off a little bit. To show how this tapers, let me show you the linear part of this equation. And that dashed line is the function 33 plus 0.067 times W. So what you see, this last term is the tapering. What is this capturing? Why is it there? Well, what it's saying is, if I have a 250 kilogram shipment and I add 1 kilogram, that will not affect the cost as much as if I had a 50 kilogram order and I went to 51. So it's saying that the marginal increase decreases over time. This happens a lot in practice, and when we do regression, we will use this. So what we're capturing here is that a quadratic equation can capture the way prices and other things behave in practice. And in this case, this quadratic equation, we wrote it in a slightly different form. The A value is the negative 0.00005, the B is 0.067, and the C is 33. The sequence with which you write the equation doesn't matter. Just make sure you understand what the A term, the B term, and the C term is. So these are two examples of using the quadratic in practice.